All right, folks, this is lesson number 3 for our electricity unit. It's where we're really starting to dive into the electricity concepts that are behind circuits. So we're going to start to see this really directly relating to the project that you're working on. Today's lesson is on current, Ohm's law, and electrical power. So our 3 basic goals for this unit are to define a few terms, first current and then resistance. These are 2 essential concepts to understanding how circuits work. Next, we're going to start relating those things using Ohm's law, which is like the mother of all electricity formulas that you will encounter in this unit. And the last thing that we will look at is electrical power and how to calculate it. All right. So just a reminder on potential difference and electric potential. Right? Now when we have 2 points that are at different electric potentials, we know that's going to prompt any charges caught in between those 2 points to move. If you recall, positive charges will move from the area of high potential to the area of low potential. One way to think about it that may help you is to think of potential as kind of like pressure pushing on those charges. The same way that we find that molecules and particles tend to move from areas of high pressure to low pressure, in the same way we find that at least positive test charges will move from areas of high potential to areas of low potential. So that's another way to kind of think about what we mean by potential and why this whole issue of having a potential difference matters so much. Okay, so by having a potential difference, we're sort of exerting pressure on our charges to get them to move from one place to another. As they do so, obviously, our charges need a path to follow from point A to point B. Now, once we get our charges moving along a certain path, we can measure something called current. Now, current basically just means the flow of charge, but more specifically, if we want to go about quantifying the intensity of that flow of charge, what we can do is look at how much charge passes a single point each second. Okay, so we can kind of think of it almost like velocity, but instead of looking at how many meters are being traveled per second, we're looking at how much charge is passing a particular point per second. Now, the units that we use to measure current are called amperes, which is represented by a capital A. 1 ampere is the equivalent of 1 coulomb passing a point per second. Okay, so again, 1 coulomb of charge passing per second, that's equivalent to 1 ampere. Now you might have guessed then that the way that we calculate current is simply to take the charge measured in coulombs divided by the time measured in seconds. When we divide those two, we end up with our current measured in amperes. Now a sample problem to see how we're doing with this. We can imagine that we are shooting a current at a plate of something. That current measures to be 2.5 amperes. In other words, 2.5 coulombs pass a given point along that path each second. Now we're going to shoot that current at that plate for 1 minute straight. We want to figure out how much total charge has accumulated on this plate as a result of that current. So here's what we know. We know the current, or the rate at which the charge is flowing, is 2.5 amperes. We know that the time elapsed is 1 minute, but if you recall, amperes is equal to coulombs per second. So we need to convert any time that we use into seconds. So 1 minute is equal to 60 seconds. That's the time that we'll use. We want to solve for Q, the charge. Now current is equal to charge divided by time. If we're solving for charge, all we have to do is multiply both sides of the equation by time. And then we just plug everything in. Plug in our current, plug in our time, and we determine that a total of 150 coulombs of charge has built up on this plate over the course of 1 minute. Okay. Now there are 2 types of current that we can run into, DC and AC. Ever hear of AC/DC? Ah, now you know, they're physics nerds. All right, so direct current refers to a situation in which charges are only moving in one direction. It's like a racetrack. They're all going the same way, all going clockwise or all going counterclockwise. You don't have any weird black sheep running opposite the flow of traffic. Now, alternating current, AC circuits, on the other hand, have charges moving back and forth. And the reason for this is because the potential difference is constantly swapping back and forth. So the electrons will run one way, and then the potential difference will swap, and so then they'll run the other way, and then they run back the other way, and so on and so forth. Now, to help you visualize this a little bit better, we've got another simulation. Look at that. All right. Now, this circuit on the bottom is powered by a battery. In a battery, we have one plate that always is going to have the higher potential and one plate that's always going to have the lower potential. All right, so this would be an example of a direct current circuit, a DC circuit, because our potential isn't swapping at any given point. So when I turn on this circuit, we see that the charges continually move in the same direction. That's an example of DC. Now, in this circuit, we have an AC power supply, and basically the outlets in your home will work this way, where we've got changing potential differences between the 2 points that our charges can flow between. Now, notice that when I hook this one up and complete the circuit, the charges are constantly moving back and forth. So 1 minute this side is the lower potential, and the next second that side's the lower potential. So they're constantly waffling back and forth, going back and forth between those two sources. All right, so alternating current, direct current. Now, I've been asked before if lightning or if electricity is hot or warm. And the answer is no, not inherently, but we'll often find the two coming together. Now, here's why. I'm sure you've noticed that if you have traditional incandescent light bulbs in your house, if you leave them on for a while, they'll get hot. You don't want to grab a light bulb right after it's been turned on for a while because you will get burned, and that would be dumb. The reason that we end up with a situation where we started with electrical energy and somehow ended up with thermal energy is that some of our electrical energy ends up converting into that thermal energy because our electrons are trying to move through due to that electrical energy. But let's face it, in our filaments in the light bulb, we've got a bunch of atoms that are kind of just sitting there in the way. So as our free electrons try to push their way through, thereby, forming this current, they're constantly running into these atoms. You can almost think of it as there's some sort of friction along that current path. So as our electrons are trying to move from the area of low potential to the area of high potential, in the case of electrons, they keep running into these atoms along the way in whatever medium it is that they are traveling through. Now, as they run into it, again, much like friction, some of their electrical energy, the energy that they have just by moving through and creating this current, gets diverted and transformed into thermal energy, which is why then we find heat radiating out from this electrical device. Okay, so basically then what we find is that electrical energy is going to transform into thermal energy anytime we've got something opposing the flow of charge. Okay, and typically when we talk about something opposing that flow of charge, we're talking about the arrangement of atoms in the wire or in the rubber or whatever material it is that we're trying to get charge to flow through. Okay. Now, not all materials are equal in terms of how much they oppose the flow of charge. Okay. So what we can do to determine how much our atoms in our material are going to get in the way, or in other words, how much we're going to oppose the flow of charge, how much electrical energy is going to be converted into thermal energy, so we can look at something called resistance. So resistance is just a measure of how much opposition there is in our material that's going to prevent the flow of charge or the flow of current through that material. Now we measure resistance in the unit ohms. Now ohms, you can see we kind of ran out of Roman letters for use as our variables here. So we had to turn to the Greek alphabet. So we've got our ohm symbol right there. Look at that, kind of like a horseshoe. All right. So this is the unit that we measure the resistance in. Okay. Now the reason that conductors tend to pass charge along so easily is because they have a very low resistance. The way the atoms are set up inside of them, they're pretty open to letting our electrons pass through easily. Okay. Insulators, on the other hand, have a very high resistance. Their atoms are arranged such that it's very difficult for electrons to travel through and continue that flow of current, which is why insulators tend not to be very good at allowing current to pass through, whereas conductors very easily let current pass through. It's all about relative resistance levels. Okay. Now, we get to Ohm's law. Now remember how Newton's second law, F equals ma, I told you was like the end-all be-all of mechanics equations, and if you only remembered one, you should make it Newton's second law. Well, for electricity, Ohm's law is where it's at. This is the fundamental equation that's going to drive all of your circuit analysis. Now what Ohm's law does is it relates electric potential difference between 2 points, the current flowing between those 2 points, and the resistance of the material between those 2 points. Now what we find then is that the potential difference, V, is equal to the current running between those 2 points times the resistance. Okay? So what that means then is if we have a given potential difference, so V stays constant, and this will happen anytime you just have one battery powering everything, the same battery always the same potential difference between our 2 points, we will find that as we increase the resistance between those 2 points, the current will decrease. Okay, so one way to think of it is kind of like water flowing through a pipe. If you recall, the electric potential difference, V, we said was kind of like pressure, the amount of pressure pushing that water through the pipe. You can think of R as the amount of gunk that's built up in the pipe that's kind of blocking the flow of our water. So it makes sense that for a given amount of pressure acting within our pipe, the more gunk we have, more resistance, kind of blocking off our pipe, the slower the water's going to flow, the slower the current's going to be. Okay. Now, to practice using Ohm's law, a simple sample problem. We've got a circuit set up with a 9-volt battery. Along that circuit, we've got a 3 ohm resistor. We want to figure out then what is the current traveling through this circuit? How quickly are our charges going to flow from one side of the battery to the other side of the battery? So I know that my potential difference between the 2 plates of the battery is 9 volts. I know my resistance is 3 ohms. I just need to figure out my current. I've got Ohm's law to help me because Ohm's law is my best friend in this unit. I'll rearrange it to solve for I by dividing both sides by the resistance, and then I just plug it all in. And hopefully you know that 9 divided by 3 is 3. So we end up with our current as 3 amps. All right, last topic to talk about, electrical power. Okay, so anytime we're using some sort of electrical device, we're converting that electrical energy stored up in the grid into something else. It might be light, if we're talking about a light bulb, could be heat, sound, something that moves, whatever. Okay, so when we talk about the power rating of that device, whether it's a light bulb or a blender or your TV or whatever, what we're really looking at is the rate at which energy is being drawn from the grid and transformed into whatever form of energy it is that you are trying to get your device to put out. Now we've run across the term power before. Last semester we talked about how power was the rate at which work was being done. And work, if you recall, is just a transfer of energy from one object to another. So when we talk about power, we're talking about the rate at which energy is being transferred or transformed. Okay. Now what we can do then is calculate the power by taking the current, which basically is telling us how quickly charges are moving through. It gives us a sense of the rate there, times the voltage, which gives us a sense of the sheer amount of energy being drawn out from the object. So the power is just going to be equal to the current times the voltage as a way to measure how much energy is being drawn out per second. Now a sample problem to kind of show you how this works. Let's say you've got an appliance. It has an overall effective resistance of 10 ohms, and we measure that it draws 9 amps of current. We want to figure out what's the power output of that appliance. What rate is energy being consumed by that device? So I know my resistance is 10 ohms. I know my current is 9 amps. I just need to figure out the power. Now the equation that we have for power is current times voltage. I've got the current, but I do not know the voltage. So before I can solve for power, I have to solve for voltage. But we've got Ohm's law to the rescue. So Ohm's law tells us that voltage is equal to current times resistance, both of which we know. So we determine then that the voltage is 90 volts. Now we can plug that into our power equation and determine that our device is drawing 810 watts of power. In other words, 810 joules of energy per second. Kind of a lot. Now here's our little check-in questions to see if you really got it. This first question is a little tricky and involves a lot of different things, so I want you to really think carefully about this one. Now you may know that there's recently been a shift in terms of the kinds of light bulbs that people are suggesting that we use. There were the old incandescent light bulbs, which are the light bulbs that we always think of, the big bulbous sort of light bulbs. But there's recently been a shift over to these compact fluorescent light bulbs, or CFLs, which are a little bit more squiggly. So we have two different options in terms of the light bulbs that we can use to provide light in our house. They draw approximately equal current, but one thing that you'll notice if you use these bulbs is that the CFLs don't get as hot as the incandescent bulbs. You can leave them on for a while and they're still not too hot to touch in general. Now people are all talking about how great CFLs are. The question is why? I'll give you the hint that it has something to do with the amount of energy they each consume. Okay. Second question to check in. We've got two circuits. They're each powered by a 1.5 volt battery, so we've got the same voltage for each one. Circuit 1 has 10 ohms of resistance. Circuit 2 has 22 ohms of resistance. We want to figure out which circuit has more current running through it. In other words, which one has our charges moving faster throughout our circuit. So take a moment, think about it. Don't just look ahead. Think about it. And when you're ready, continue on. All right. So the first question on CFLs versus incandescent light bulbs. So the fact that our CFLs don't get as hot tells us that they have lower resistance, because if you recall, the higher the resistance, the more that device will convert our electrical energy into thermal energy. In other words, the less efficient it is. All right. So the fact that the CFL doesn't get as hot means it's got lower resistance. It allows the current to travel through pretty easily. Now, the fact that it's got lower resistance means that we don't require the same amount of voltage between the 2 points on the light bulb where the current is passing through. Okay. Now, having less voltage and equal current means that there's less power overall drawn by the compact fluorescent light bulb, which means that there's less energy being drawn out per second. Okay. This is why we tend to think of CFLs as being a greener option, because they don't waste as much energy. We're really getting full bang for our buck here by taking as much of the electrical energy from the grid as possible and converting it into light rather than inadvertently converting a lot of that electrical energy into heat the way that incandescent bulbs do. Also good for your electric bill, just FYI. Okay. Now for the second question, if you recall, circuit 1 had 10 ohms of resistance, circuit 2 had 22 ohms of resistance. Now, thanks to Ohm's law, we know that V equals IR. In other words, the lower the resistance is, the higher the current is. Therefore, circuit 1 is the one that will draw more current, that will have the charges moving faster through because we've got less resistance blocking the path of that current. That's all I've got for you today, folks. Thanks for listening.